Today we're going to talk about writing the equation of a transformed parent function. You should have a worksheet with you called worksheet number 1 on writing equations of transformed functions. So you can see there are 4 transformed functions on the front, and there are 4 transformed functions on the back. And we're going to be writing equations of each one of those. So what you're going to do is you're going to follow this 4-step method to make it easier to actually write the correct equation of each one of these transformed functions. And here are the 4 steps. The first thing you're going to do is you're going to draw a new XY axis with a straight edge. And this new XY axis will have 0, 0 be at the vertex of the transformed function. With the vertex of the graph at the new 0, 0 point when you've drawn your new XY axis. And this is what I mean by step 1. If you take your worksheet and you look at this function, the vertex of this parabola is right up here at the point 4, 5. But what we're going to do is we're going to ignore that, that x and y axis that's drawn on here, and we're going to draw our own xy axis with a straight edge. So that 0, 0 corresponds to the vertex of this parabola. So here's my new y-axis, and here's my new x-axis. So now we're just going to forget about the original xy axis, and we're going to use this new one that we've just drawn. I'm going to try to draw it a little bit darker so you can see it better. All right, so this point right here corresponds to 0, 0. This is the new xy axis. So this point right here would be 1, 1. And this point over here would be negative 1, 1. And if I were to draw just a normal parabola on this set of xy axes, we'd have 1, 1, 2, 4, 1, 2, 3, 4, and negative 2, 4. So a parent function would look like this, but what we want to do is we want to try to get the equation of this transformed function down here. So we move on to step 2 after we've drawn our new xy axis. Step 2 is just to determine the vertical and horizontal shifts. And just to keep ourselves organized, we'll just call it VS for vertical shift, and we'll give it a number, and we'll say the horizontal shift is whatever number it is. So on this particular example, when we do step 2, we can see that we have moved our XY axis to the right by 4 and up 5, because that's the vertex of our transformed function. So the horizontal shift would be right 4. The vertical shift would be up 5. So I'll just write that down here. The horizontal shift is right 4, and a right 4 would correspond to a minus 4 next to the x variable. The vertical shift has gone up 5, and up 5 would be indicated with a plus 5 at the very, very end of our written function. Step 2, done. The next step, 3, is you're going to pick the point closest to the vertex that has definite x, y values that you can determine. Pick a point closest to the vertex with definite x, y values. What I mean by that is don't pick an xy point that has some fractional xy value. Pick something that's going through a definite xy value that you can tell from the graph. And then when you pick that point, you're going to call it AB. And what I mean by that is when you look at this particular example here, and you look at this graph, and it looks like you can pick this point right here. The original point would have been 5, 2, but we're not going to call that 5, 2 because we have a new set of xy axes. What we're going to call this point, based on our new xy axes, is we're going to call this 1, negative 3. So I'll just write that down here, 1 comma negative 3, and those are our A and B values. So the A and B, the AB point, the closest point to that vertex, is equal to 1, negative 3. Again, based on our new xy axes. And then we move on to the last step, step 4. Step 4 says that whatever the A value was, you're going to divide x by it, and whatever the B value was, you're going to be multiplying the entire function by it, or in other words, multiplying the y by it. So divide the x inside the function by A and multiply outside the function by B. And you'll get something that looks in general like this. Y is equal to the whole function gets multiplied by B. Inside parentheses, you're going to divide the x value by A. And this is really important that you open up parentheses before you have the x. So you're dividing x by A, and then you're going to do either a plus or minus the horizontal shift. If it's been shifted to the right, it will be minus. If it's shifted to the left, it will be a plus. Close up your parentheses, close up your parentheses again, and whatever the parent function is, maybe it's a squared, a parabola, maybe it's a squared value, maybe it's a cubic function, so you'd have a cube here. Maybe it's a square root function, so the square root would go between the b and the 1 over a. Or maybe it's an absolute value function, so you would have absolute value bars where these outside parentheses are. And then you have to consider the vertical shift, so you're going to do plus or minus at the very end of the function, a vertical shift, and plus means up, minus means down. And so I'm just going to put a little box here because this box could mean squared, cubed, absolute value, square root. In our particular example here, we determined A and B to be 1, 3. So what we're going to do is we're going to write our equation is y is equal to negative 3 times, now you don't have to divide by 1. You don't have to say 1 over 1. It really, it doesn't matter about having a coefficient of 1. So it's going to be negative 3 times x minus 4 to the second power, it's a parabola, and then plus 5. And that's the end of that problem. And what I always do, just to make sure I'm right, is I like to plug it into my graphing calculator and make sure that the points on my graphing calculator match the graph. So we're going to plug in y equals -3 times parentheses x minus 4 to the second power plus 5. Take a look at the graph. Hopefully it will look like what we were given. And then hopefully when we look at the table of values, we can go down through some of the definite values that are on our parabola, like 2, -7 is on our parabola, 4, 5, 3, 2, 5, 2 is on our parabola, and 6, -7. So these table of values match up with the graph that we see. This takes a lot of practice, so we have 7 more to practice with. And let's see how many we can get through. The second example is an absolute value function. So my first step is to draw new xy axes at this vertex. The second thing that I'm going to do is determine my horizontal and vertical shifts. So my horizontal shift, it has been moved to the right by 3. I'll just put an R3 for right 3, and that means we're going to do a -3 inside the parentheses. The vertical shift, it has gone down 4. So we're going to have a -4 at the end of our function. The next thing I'm going to do is I'm going to pick a definite point that's closest to this vertex, and it looks like it's this point right here, which is the old 4, 0, but with our new xy axis it is over 1 and up 1, 2, 3, 4. So this new point would be 1, 4 if we use these xy axes. So our a and b values are equal to 1, 4. And now all we have to do is write the equation of this absolute value function because we have everything we need. So the absolute value function would be y is equal to 4, because the y value is multiplied by 4, that's b, and it is an absolute value function. Since this value right here of a is 1, we really don't have to consider it in our equation. Because it's been moved right 3, we say x minus 3, close up our absolute value, and do a -4. We'll check that in our graphing calculator, make sure we're okay. 4, math, num, absolute value of x minus 3. Get rid of this old stuff. And then -4. And take a look at this set of xy values on our table, and it looks like 0, 8 is on our graph, 1, 4 is on our graph, 2, 0, 3, -4. It looks like we're okay. So there's the graph. I'm going to do a zoom 6 so it'll look like the paper. All right. Next one we have is a cubic function. So it looks like the vertex is right here. And when we draw our new xy axes on that vertex, we can determine the vertical and horizontal shifts. It looks like our horizontal shift has been moved to the right 4. which means a minus 4. It looks like our vertical shift has been up 2, which is a plus 2 when we write our equation. And if we pick the first point that we can see definitely, it would be this one all the way up here. So considering these as our new xy axes, this is over 1, 2, 3, and up 1, 2, 3, 4, 5. So this value would be 3, 5 if we were to use these as our xy axes. So our a and b values are 3, 5. And now we're ready to write our equation, which goes like this. Y is equal to 5 times 1 over 3. Open up parentheses. You really need these or else your graph won't be right. And the x value, you have a horizontal shift right 4, so it's minus 4. And then you have double parentheses here. It's cubed. And then it's been moved up 2, so it's plus 2. This is really important. If you don't have these inside sets of parentheses around this horizontal shift, it won't be right. So what we're going to do is we're going to put that into our graphing calculator and make sure that it matches our graph. 5 parentheses 1/3 parentheses x minus 4 double parentheses to the 3rd power and then plus 2. So when we graph that, we'll see that it looks like it is right. And when we look at our table of values, 1, -3 is a point on our graph. 4, 2 is a point. And 7, 7 is another point on our graph. And oh, there's one more. I think we can tell for sure. No, I guess not. So those 3 points definitely you can see. The next function is called a step function, or the greatest integer function. And it's hard to see on this graph, but this has a little segment here. All the right-hand parts of these little steps have an open circle on them, which the graphing calculator can't display, and the left-hand points are all filled in circles. This is, again, it's called the greatest integer function. And the parent function is y is equal to, and here's the notation for the greatest integer function. It's kind of like brackets, but it's got these extra little bars in it. Greatest integer. If you want to look at it, just the regular parent function on the graphing calculator, you can just press y equals math num option 5 int of x. And then when you graph that, you can see the little steps going up through. The vertex of this is at 0, 0, and the length of these little steps all have a length of 1, and the distance between each one of these steps is also 1. So when you have something transformed like this, the normal parent function, like I said, has a vertex of 0, 0, but this has been shifted to the right by 1. So it's got a horizontal shift, move to the right by 1. So that's going to be a -1 inside the function. It doesn't have a vertical shift because all that's done is it's been moved over. And then the distance between these, instead of being 1 apart, these are all 2 apart. So it actually has a vertical stretch of 2. So I'll just call this a vertical stretch. This one's a little bit different than the other functions. Is equal to 2, just because the vertical stretch just gives the distance between each one of these steps. So when I write this function out, I'm going to just call it y is equal to 2 times the greatest integer function of x minus 1. And there are other things. You can actually call this a shift down of 2 if you wanted to. And the equation would be y is equal to the greatest integer function. It has not been shifted at all to the left or right, but it has been shifted down too. So either one of these equations would be correct. You can put those in. Y equals, I'm going to insert a 2 in front of that, and I'm going to call that a -1 because it's been shifted to the right. And when you graph that, you can see the distance between the steps are all equal to 2. And it matches our graph, greatest integer function. All right, let's just finish up these last 4 graphs. Now these, it's kind of hard to tell where the starting point is, but on this one, the starting point of this square root function is at -2, 3. And then the first point that's not at the vertex is this point right here. So we'll draw our new xy axes at this starting point of the square root function. So the shifts are, you're going, this square root function has been shifted horizontally to the left 2, which is a +2. The vertical shift, it has been moved up 3, which is a +3. And the a and b values, the very first point that's not on the vertex is up 1, right 2. So, sorry, right 2, up 1. So 2, 1, over 2, up 1. So when you write this square root function, you're going to write it as y is equal to, you don't have to have a 1 on the outside of this function, so you can start right out with the square root of, and the b value is, or the a value is 2, so it's 1 over 2 times x. Horizontal shift is +2, and because it's been moved 3, up 3, you'll have a +3 outside of the square root function. And if you wanted to distribute this 1/2 through the parentheses, you can, but I like it looking like this because I can definitely see what's happened to the x values and what's happened to the y values at the end. So y equals the square root of 1/2 parentheses x plus 2, and then outside the parentheses, or outside the function, +3. And that looks like our original graph. If you wanted to check the table of values, you'll see that that table of values will match what's on that graph. The next one, here's another square root function. It's kind of hard to tell the starting point, but this starting point down here is at -4, -5. So we'll draw in our new xy axes. -4, -5. And it looks like the first point, definite point that we can pick out is this one right here. Oh, let's put our horizontal and vertical shifts. Our horizontal shift, it's been shifted to the left 4, so -4. The vertical shift, I'm sorry, +4. And the vertical shift has been shifted down 5, so that's a -5. And the a and b value, the first point is over 1, up 3. 1, 3. So we can write this square root function as the b value is 3. So it's 3 times the square root. One won't matter in our equation. So horizontal shift x plus 4, vertical shift down 5. And that should be it. Take a look at that. 3 times the square root of x plus 4 minus 5. And that looks like the graph that we're given, and if you take a look at the XY values, you'll see that they match. The next one, our absolute value function. Here's the vertex here at 3, 2. Horizontal shift, it's been shifted to the right 3, so it's minus 3. Vertical shift, it's been shifted up 2, which is plus 2. And the A and B values, the first point that I see that is right here. So this is over 3, down 1. Over 3, down 1, 3, negative 1. And when we write this, y is equal to this negative 1 goes on the outside of the absolute value function, negative 1 times the a value is 3, so we have a 1/3. Our horizontal shift is minus 3, so x minus 3, parentheses, then you end your absolute value function. Oh, I'm going off the page a little bit. And a vertical shift up to plus 2. So let's take a look at that in the calculator. Y equals negative math, absolute value of 1/3 parentheses x minus 3 parentheses plus 2. That graph looks like the graph that we're given. And then the last one is just a linear function. I would suggest, you can go through this whole vertical horizontal shift A-B function, but I think the best thing to do would be to use the point slope formula on this. Let's pick a couple of points. This point right here is called 1, 0. Let's see, the next definite point that I see on this graph is 6, 3. So if you wanted to get the slope, 3 minus 0 over 6 minus 1. So the slope is 3/5. And then you can use the point slope formula. I'll use this point, y minus y1. Y minus 0 is just y is equal to m times x minus x1. And that's all you have to do. Y equals 3/5 parentheses x minus 1. See if that works. 3/5 parentheses x minus 1. You can distribute that 3/5 if you want to, but it's totally unnecessary. And then you can take a look at those table of values and you'll see that they all match up. So just follow those 4 steps and you'll be good. We'll practice some more of these tomorrow in class.